Okay, good morning. Welcome back to our knowledge sharing session. In the last episode, I think we had done modeling. This morning, we're briefly going to look at what was remaining. That was the after modeling, we were supposed to look at loading. From loading, then we look at analysis output and then the design. So quickly, if I take you through the first, we had the different loading. We have the self weight. This is our self weight. You have to this is the self weight. Then we have the weight concrete. That is the weight concrete. Then we have formwork. We have the formwork loading calculated. Then we have the barrier loads. You can see barrier loads are on the site. Formwork is for the whole thing, because after placing the precast, you normally have also a precast unit of about 50 millimeter to 75 precast slabs. Your unit filling in the gap to give you that to allow you to cast the concrete slab. Then additional loading is here. If you have you have utility. So in this case, let me see if I put or I didn't put. Yeah, so you can have that side utility line, and then the wiring surface here. But I can jump. Then you can have that additional load. You can do like utility on either side. Then there's also utility here. So you can think of what kind of load you think can be on one side. So you see, to balance it up, even to give you a symmetry kind of analysis. Then for the wiring surface, it is for the entire area, though you should be mindful of the effective area. And then the area taken out by the crash barrier, you don't take on that. But here for design purposes, I've allowed it to be covering full extent. Pre-stressing is not part of this. Then we have I think here we have temperature. Temperature, I think there's a minimum temperature, and also we have a maximum temperature here. Then we have temperature gradient, the temperature rise and fall. Normally this one you input as per the code or as per your, but I think from this, let me see, this here, these are the temperature stuff. This is how the temperature gradient looks like. Of course, some of this loading you have to read from a code of practices and other literature for you to appreciate in depth. Then we have water. That is water current. Some put it triangulated upward. And then for this case purpose, I considered it uniform, and using a higher value velocity of 10. I know normally most of this must be determined, but for demonstration I use 10. And then you have to basically, normally what you need to do is for these peers are subject to the experience water current as if it was aerodynamics effect. So the drag effect sometimes should be taken into consideration. As water is passing through this bridge, it tends to push and drag. So the entire formula used for aerodynamics is basically applicable here, except you've now replaced the density of air with density of water, then the speed of wind with that of water. So not something realistically. So that is what we could do in the loading. Then what would be the output of this loading? So if you want to see the output of this loading, if I do my self weight, I start from my first stage. if I look at the different action effects, then I can look first reaction due to cell of weight. That would be it. That's the cell of weight of the two pairs at 2964. What about in terms of moment? That is the moment due to cell of weight of the peer support. If the precast girders are placed in position, then definitely there will be increase in the action effects, especially now over the peer and the peer support, and also for the respective girders. And this will continue on and on up to the final stage. So these are basically loads based on materials that are input into the bridge before bringing the other loads like traffic and earthquake and the rest. So for post-processing, this is wind effect. No temperature, not wind. This is a temperature effect, and you have seen it there. It's applied, but this is how it affects the girder. If you want to see the girder in detail, this girder is in detail, you can actually activate on the girder, and then you're able to look at that. It's more into that. Looks like I've not grabbed it very well. Let me see, put it up to here. So that is the temperature effect on the girders. Then the Tmax, maximum temperature, this is how it is. Then when you go down to temperature rise, that is how temperature rise affects the girders. And then we can come to earthquake. How does earthquake affect your girder? This one has to be taken care of. And then the one in the Y direction, and then the girder in the Z direction. This is how earthquake affects our deck system. And now what we can do is to quickly look at the effect due to other loads. So if I can activate my sections, here up, put all these main girders. Okay, so if I have that, and I want to look at the effect of traffic, LM1 plus DS, that is the effect. As effect, these are lateral. These are the diaphragm, and these are the beams. And then you can look at shear force value. That's what normally you have. And then if I want to look at axial load, that is what you have. Then when you want LM2 has similar stuff. Okay, LM2 has that. It looks like the external girder is overstress, it's overloaded down the rest. So let me look at LM3 plus its shear force. That's the shear force value. So basically these are the action settlement, also has implication on our this is settlement. This is for shear and this is for the moment. So you can see these are simply supported girders, and that's how the moment due to settlement can affect. And this and this. So if your settlement exceeds 10 millimeters, definitely there should be an issue to follow here. And then for the cell of weight, this is now when the load combinations are here. Different load combination with different values are all given there. This is combination one all the way. I can just do a spot check and then look at the moment in Y. Yeah. So basically you are able to get all that you want, and then all these action effects will help you now to design. So that is for peer. Now this peer can be modeled in the way that to reflect exactly the width or the thickness, this peer value here. So this value here tend to be very high because it's assuming that this is a point, but yet this is about 6 meters. So you will spread this where the 6 meters end is where the moment can be taken for design. But for this case, this is for demonstration purposes, and so we can allow it be done that way. Okay. So this one is over exaggerated because it's not taking care of the width of the pier. So which pier is basically around here. So it means that means moment that control design will be beginning from this point going this side, because this is now where the pier ends, the 6.9 meters end. And then the shear force, that's the moment, and then the shear force will be this one here. So the shear value will be from here, this side, and then from here, this side. This one all will be taken up by moment. I will demonstrate another a model where you restrict this using the spring constant, and you're able to get that very well. Okay, so these are the action effect that you get from the different load combination, different loads and load combinations. I think that should be good enough for us to demonstrate that. So that is that. Thank you so much. I'm now going to go and demonstrate how the design output have been derived.